is, and let me give you control. Actually,
Okie doke.
let me admit everybody. Done. We'll turn off the waiting room. Now I will make you the name would quit moving around. I'll make you the controller. Does it do that to you too?
Yeah, when I'm trying to find someone.
Okay, there you are. All right. Oh, got it.
All right. Can everyone see my screen? Get the chat open. Cool.
31. You're right. There is no comma save down there. It's a problem.
Okay, doke. So in this lab, we're going to be looking at the idea of classification, which can broadly be summed up into I've got some data and I want to, we'll start with binary. Every piece of data can answer a particular question, either yes or no. So we want to go through the entire data set and apply that question. The question could be anything really. It doesn't have to be binary, but we're talking about binary right now. So what I mean by that is, let's see. Well, here, this should work. We have the data from a casino where we get the percentage of time for every machine in the casino that the players win. So we want to go through and assign a label to every machine to make sure that they're fair. So either a machine's fair or it's not. Now, how we figure that out per machine is up to, we got to do some work. Do they need to win 51% of the time? Whatever. But every machine is either yes or no, and we've got thousands of them. So what we would want to do is go through the whole piece of data and classify the machines as either fair or not fair. So that's just an off the top of my head example. Man, it's like the behind me is just glowing. Okay. So we've talked about regression quite a bit. And by regression, we mean we've got data all over the place. And we want to try to fit a line of some sort. Doesn't have, well, let's call it a curve, because a curve could technically be a line. Trying to fit a curve to that data so that we can predict stuff. So we've done OLS, looked at some errors we can try to account for. We did some confidence interval stuff, and we did multiple linear regression.
So like, I kissed her.
Just do. Oh, interesting. Wow. So what if instead of wanting to predict where the next data might be going, we want to predict, kind of like I was saying, one way or the other on our data? Is it fair or not fair? Or is it, in this case, green or teal? So that process is called classification. So regression was trying to fit a curve that has the least amount of error. And classification is, we want to be able to draw a curve somewhere that gets the most of one type on one side and the other type on the other side of the curve. So what domains might be, what domains would you use one or the other for? It kind of depends on what you're trying to ask. So regression problems have continuous and usually unbounded outputs. Examples when you're estimating the salary as a function of experience, or all the examples we've covered so far. On the other hand, classification problems have discrete and finite outputs called classes. For example, predicting if an employee is going to be promoted or not, or if the machines are going to be fair or not. There's two types of classification problems, and really, they're all the same thing. It's just that having a yes or no is so nice and so useful that we make it its own kind of type. So either our data can be one thing or another, so green or blue, or promoted or not promoted, or take your pick. Or we have multi-class, meaning there can be as many options as you wish. Now, the more options you have, the difficulty and computation time explodes. So what do we need classification for? We apply it in many fields. For example, text classification algorithms are used to separate spam emails. Other example involve medical applications. There actually exist machines, like logic machines, not they don't do anything physical. What they do, it's a program that doctors will have, and it just looks at all the data that comes in about a patient. And from that data, it can predict, and sometimes better, and by sometimes, I mean enough times for it to be significant, it can predict whether the patient has any list of stuff, predicting cancer and all that. All right. So before we get into being able to do classification, we need something that looks like this. What is this? This is called a logistic regression. So just like linear regression, which puts a line and tries to fit to the data, we are going to try to take a logistic function and do the same thing. It's easiest on binary classification because once you fit the logistic function, you're done. But you can also do it with multi-class if you really want to. Logistic regression is a statistic method for predicting binary classes. The outcome or target is dichotomous in nature, means there's only two possible cases. For example, it can be used in cancer detection problems. It computes the probability of an event occurrence, and it can be considered a special case of linear regression where the target variable is categorical in nature, meaning, so when we did like the voltage, time voltage, there's an infinite number of outputs because time goes on forever. In fact, there are more than an infinite number of outputs, but that's for another show. But what we're talking about is where the outputs are bounded, and hopefully, well, it would be nice if there's only two. Okay, so the logistic regression function predicts the probability of occurrence utilizing a logit function. So if you remember, the general regression model looks like this. And if we wanted it to be linear, we just used this part and set, the rest of the betas to 0. If we wanted it to be quadratic, we keep going with the B2 and so on and so forth. And we also had the exponential and blah, blah, blah. Well, let's use a new function. It's quite famous. It's called the sigmoid function. It's also called the logistic function. here's what it looks like. So it's 1 over 1 plus e to the negative y. So that doesn't really tell us much, but here's a visualization of what it looks like. And you can start to see why it's so nice for what we're wanting to do. Because as functions go, you got to remember this goes forever in this direction and this direction. So the vast majority of this function is 1 or 0. And by 1, I mean very close to 1. And by 0, I mean very close to 0. If anybody's had calculus, I can say that the limit as x grows large or negatively large goes to 1 or 0. So for almost all input, it's 1 or 0. Now, why is that nice? Well, we're trying to do a task where every input is either one thing or another. So this function is quite nice for that. Okay. So if we apply this to linear regression, we simply replace the y here with our regression model. So we still have 1 over 1 plus e to the negative something, but that something is what we've been using. And remember, we don't have to use all of it. We can use however much we want. We can use B0, B1, we can go all the way to B2, however much we want. Now here is a visualization of the difference. So pretend for a moment that our data can only be one of two things. It's pretty obvious. You got 1, 2, 3, 4, there's 6 of whatever this kind is, and there's 6 of whatever this kind is. They're all lined up in a nice little row. Well, if we apply linear regression, this is one of the, I don't know if I'd call it a weakness. It's just there's a dot in the bottom left and the dot in the bottom right. They offset. This one offsets that one, blah, 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 blah. They all offset each other to the point to where the line goes through the middle. And it's not super useful to tell us what's what on each side of the function, because these 3 would be in the same group as these 3, which isn't what we want. However, the logistic regression works much better. It goes in there and very accurately. It's good for binary stuff. What can I say? Now, one moment, I need to download a file. The CSV I was looking for wasn't where I needed it. Funny enough, I think I actually still have one from last semester. Okay. All right, that's all fine now. Okay, doke, where were we? We were here. Let's do an example. We're going to take some data about people. Looks like this. Where does this data come from? It's real data. It's not just made up. Although, in some fashion, you could say all data is made up. So this is from the National Institute of Diabetes and Digestive and Kidney Diseases. The objective of this data set is to predict whether or not a patient has diabetes based on a certain diagnostic measurements. So the data is constrained so that the population it's being taken from is similar. In this case, all patients are females, at least 21 years old, of Pima Indian heritage. I don't know exactly what part of the world this is in. The data set has a couple predictor variables and one target variable. So that's the outcome. So the predictor variables are everything we have over here. So pregnancies, glucose levels, blood pressure, insulin, BMI. And the outcome is 1 or 0. So diabetes or not. let's see if we can build a model to predict whether or not our outcome for each patient. So we need all of our stuff as usual, and we're going to make a data frame as usual. We renamed the columns so that they're easier to look at. In the original one, just having column names that go off the screen is kind of a pain. All right, so here's the first 5. This lets us know that the data frame actually did something. Looks, decent. There's numbers. We've got, all the fun statistics, mean, standard deviation. Can't really say a whole heck of a lot about it right now. The main use for doing the head and the describe is I want to make sure my data is good. I want to make sure it's not junk. Like it didn't get messed up. Looks fine. All right, let's do some histograms. Okay, so we're going to go through each predictor variable and just take a look. Okay, it appears, makes sense, I guess, that if we look at the number of pregnancies per each patient, most of them are in the 0. And as the number grows large, the number of patients who have that number is small. That's amazing. That's a lot of kids. Oh yeah, sorry, I didn't see that. Jackson put a link in. I got it from here. Okay, next predictive variable, glucose levels. So this looks a lot more like a normal distribution. There is something near the middle that appears to be the mean, and you've got outliers, and the further you go out, the rarer it gets. Someone just doesn't have any blood or something. That's weird. This is probably an error, I would guess. Having a glucose of 0, I don't know if that's possible, but I'm not a doctor. Not yet, at least. Let's see. Label. That's amazingly useful. Wonder what label's for. Oh, that's the output, right? Yeah, that's the output. So this is apparently the known data for diabetes or not. Okay. Here we have a, I forget exactly what this thing's called. It says joint plot, but there's a name for it. It looks like a topography graph, map, whatever you want to say, of the glucose levels. So you can see the clusters of the, we have the likelihood for diabetes here on the left. And we have the glucose levels here. So there, we got a group around 100, well, centered around, and we got a group centered around what, like 120 or something? Okay, so here we need to divide the given columns into 2 types of variables. We got the target variable and the feature variable. So the predictors, the things that can tell us the thing we want to know, well, that we can use to predict it, and then the actual thing we want to know. So label is the target variable. Everything else are the features. So we're going to divide the data set into a training set and a test set. What the heck does that mean? Well, the way this process works is the model doesn't know anything to start with. So in order for it to start learning what might be diabetes and what might be not diabetes, it needs to see an example. So I feed it an example and I say, hey, this one is diabetes. It's like, okay. And then I say another example. It's like, this one isn't diabetes. It's like, okay. And the more I feed it, the more the the program starts to understand, okay, I'm starting to see a pattern in this way. And then it also needs to say, well, okay, I have what I think to be a pattern. I have a way, let's see, what's the way to say this? I think I have a way to recognize a pattern, is what the program says. Not literally, but in this example. Now I need to test it on some data to make sure this pattern recognition actually works. So what I'm going to do is I'm going to take all the data and I'm going to split it into two parts. Sorry if the dogs are being picked up. I'm going to split it into a 75-25 split. I'm going to use 3/4 of the data to train my model, and then 1/4 of the data to test that model, see if it's actually any good. All right. So we have the data set for our target. And then what we do is, you don't really need to memorize any about this syntax, because most of the time you're just going to copy and paste it. Sklearn has the built-in ability to split our data into test and training. So we're going to choose a 75-25 ratio. Might change this a little later just to see what it does. And then we're going to fit and run logistic regression, do the fit, and predict, see what we get. All right. Now, you may notice all this red stuff all over my screen. It's just warnings. They're not errors. All right. So I wonder if this is the best time to talk about this. I'm going to skip ahead a little bit just so we can see what the output of what we just did would look like. Now, the output we actually get looks like this. Now, it's kind of weird, right? Well, it's not once you understand what it actually is. This is a 2D matrix. And there are 2 elements to each axis, because our data is either diabetes or not. So here we have what we say is predicted by our model. The training data I gave to the machine, it made a model that it thinks is good. And with that model, it said, I predict that 115, wait, no, it's not exact. That's not how it works. The way this is read is 115 of the patients that were predicted to not have diabetes actually didn't have diabetes, because this axis here is the actual outcome. Get my annotation. All right. So we predicted a 0 on 115 patients that were actually negative. So we predicted negative for 115 correctly negative ones. We predicted 25 negatives for patients that were actually positive. And just the same way, we predicted 37 positives on people who were actually positive and 15 positives on people who were actually negative. So if your model is perfect, I guess, these two will be 0. And the number of people you make mistakes on will be 0. Okay, so that is a preview of what it actually looks like. Now let's talk about, now I got some errors here. Now how's that, what's going on? Well, let's talk about what those errors can be. All right, there are a lot of issues you can run into. I don't remember if I gave this lecture this semester. I don't think I did. This is the issue of false positives when it comes to anything really, but it was especially relevant last semester due to all this COVID stuff. But the percent, I don't remember if we actually have a good example of this in the class. I think we do at some point. But if you have a test that's like 99% effective, that does not mean that you've got a 1% chance of the test not messing up. It is really deceptive how often you can run into an error. And what kind of errors can those be? Well, if you remember that graph we just looked at, there's 4 categories. We have a true negative, meaning we have a correctly predicted negative. We have a true positive, correctly predicted positive. Oops, I think I double clicked. I swear the amount of time it allows you to double click is too long. And then you have false negatives and false positives. So this is like, and this happens all the time. The test, this is the reason you do the test like 3 times. You do the test and it says that you're negative when you are in fact positive, or you get a false positive. We usually evaluate the performance, comparing the actual and predicted, counting the correct and incorrect predictions. A confusion matrix is a table that is used to evaluate the performance. That's what this is. It's a confusion matrix, hence the label. Okay, so what we have here is it's just like a cheat sheet laying out not only the kind of errors you can have, but how you can calculate what the rate of getting them is. So for example, let's say this one here is the probability of a false alarm. You take the sum of the false positives divided by the sum of the condition negatives. So it's the ratio of how many of my negative guesses were incorrect. Now, this looks really mathy and confusing, but it's really not. Like true positive, predicted positive. That's just saying, take everything I predicted to be a positive. So all my predictions of diabetes, and just get the ratio of how many were actually correct. Okay, so we have a couple measures here that are nice for classifiers. Like consider your test. You can go to the doctor for some illness. It could be COVID, could be whatever. We want to say how precise is that test? How accurate is that test? What's the recall rate on that test? So these are measures that are applied to actual tests themselves, not the patients. The most straightforward indicator is the ratio of the correct predictions to the total number of predictions. So you take the number that were correct and compare it to the total number you guessed. So that gets us the accuracy. The extent or how important recall and precision on depends on the problem. Achieving a high recall is more important than getting a high precision in cases when we would want to detect as many heart patients as possible. So if you think back to, I don't remember exactly the first time somebody talks about this. For me, I think it was chemistry. The difference between accuracy and precision. If I am accurate and I need to hit something inside this target, all right. I've got all my shots, most of my shots inside my target. I'm pretty accurate. However, to be precise, I need them all to be very closely grouped. This is also, this is a literal representation of target shooting. So you can be precise but not accurate, meaning my grouping is very small, but So my results are going to almost always be similar for a given input, but they could be correct or incorrect. Accurate, meaning they are inside the target area. So in cases where it's heart disease, we care more about precision than we do about recall. However, when classifying whether a bank customer is a default or not, it's desirable to have a high precision since the bank wouldn't want to lose customers who are denied the loan based on the prediction. Now, this is a whole bunch of theory, and I don't want to overload everybody. So let's look at the output again. So these numbers right here are what's actually shown here, just not visual. This is kind of the output for a yes/no classification, binary classification. Okay, let's actually apply those measures to our test to see how good it was. How can we know how good it was? Well, remember, we split the data up, 75-25. So I can use that 25% of the data to test my model to see if it's good. This F1 score, the formula for it's right here. It's kind of like that. Well, suffice to say that the F1 score, it's just something that has turned out to be useful. So, yeah, kind of like it says here, if you aim for a good F1 score, everything else kind of falls into place. So for us, we had a accuracy of about 80%, well, 79%, precision 71, recall about 60, and our F1 score is 65. Is that amazing? I don't know. It's kind of hard to say. They're all above 50, which is okay, but if this were life or death, I don't know. I'm not super happy with it. Here is those numbers for the actual for 0 and 1. So these are their accuracy, precision, and recall for the test itself. This is the specific for negative, positive. So it can very likely be the case that your test is more precise for a negative than it is for a positive. And that's what it's talking about here. All right, let's do another example. Okay, we've got some credit card data about, we're trying to detect credit card fraud. So I suppose, yeah, I'll have to go get that. I'm going to pause while I go get the data, because data is useful. I don't appear to see that data. Someone tell me, am I blind? Is there a link to the credit card data that I'm not seeing? One moment. I think actually, that might be it. Let's try it. It won't let me. It wants me to make an account. Okay. I have gotten a message that Dr. Cleveland's working on it. I'll run through what we're going to try to do, and then once the data is actually here, we'll just blitz through it. Okay, same thing we're going to do. Oh, actually, I know what we can do while that goes on. We are going to change. Yeah, thanks, Parth, but I think he's on it. We're going to change our numbers. All right, we did a 3-to-1 split. Let's try changing this and make it that one. And see what happens. Let's see, I think our numbers went up. Let's see if the numbers here change that much. So we get a little bit better results by changing the ratio for our test versus training data. I made it 4-to-1 instead of 3-to-1. Let's make it something silly. I'm going to do half and half. This is why it's important to choose a good ratio for. Yeah, we went very much down on that one. Now, what would be the worst possible outcome? If I did this, I don't even know if it'll work if I do that. Yeah, it won't let me. Oh, shoot. I had it on pause. I'm sorry. I was changing the number. It's just me talking to nothing. I was changing this number here. It started out as 0.25, and I changed it to 0.2. So instead of 3-to-1, it's 4-to-1 now. And the numbers we got are better. Not by much, but it's still better. And then what I did that was silly is I changed this to 0, and it wouldn't accept it because it has to be actually between 0 and 1. So I can make it something like this, and I'm saying I want 99% of the data for one thing. So this should be really not very good. We only predicted 4 things. Well, I guess 8. But for those 8 things, we were really on the money. Okay, so let's run through what we're actually wanting to do here. Same thing. I need my data into a data frame. Cool. It just so happens that the data we're going to have is going to have some nulls. So we want to get rid of that. We're going to check to see if there's any nulls. And if there are, we just don't want them there. And what we're going to do is we're going to make our classes the target variable and then everything else. We're going to do a 70-30 split this time. So kind of like we were talking before, what I was just fiddling around with, we're doing 70-30 instead of 75-25. And then it's all the same copy and paste, really. We're going to do the fit, the regression, well, I guess in the other order, regression, then the fit, and we're going to get our confusion matrix right here. So I'm going to check that link to see if I can just make a dinky account and get it downloaded. Uno momento. I got to do a CAPTCHA. I got to do another CAPTCHA. You know, when you get a CAPTCHA, the reason, well, why is it free that I have to do this service? It's because every time you do a CAPTCHA, you're training somebody's AI. So either you're doing text recognition or image recognition, but you're doing some work for somebody. That's why I don't like CAPTCHA. Not only is it annoying, but if I'm going to train somebody's AI, I should get paid for it. Okay, download. Here we go. I think this should work. Let's find out. All right. We got stuff. Cool. All right. This is showing the amount of nulls. We got none. That's nice. Some numbers about the data. Again, I don't expect you to be able to look at this and get much out of it, except that there's data there. All right, what do we got? So according to the actual data, meaning this is the truth rather than what we're going to try to predict, I don't know if I can. It's the link that Parth gave me. I had to make a stupid account, then I was able to download it. I am, I'll have to, for the purposes of this lab, I'm okay if you don't, if you just do the parts that don't require it. So like the first half. Because I don't want to make you all have to go make an account on this site. Not that it's good or bad. I don't know anything about it. Okay. So this is all the same stuff we did before. We are just, instead of when we made the feature columns, So here, these are the predictors, and this is the target. These are the names of those columns. We're doing the same thing here. At our predictors, so everything that's not the class column, and then the target. All right, we're going to split into the 70-30, and we're actually going to run it now. See how it goes. Okay, finished. Let's get, all right, we had, it's a bunch. So we had 76 false negative and 59 false positive. Let's visualize that a little bit. That's a lot. Our accuracy is quite nice. Let's look at the other ones. Not as super, but 99% accuracy is something you can brag about. Here's the specific details. So we are 100% accurate. Wait, no, we're 100% precise on testing for negative, which makes sense. We're trying to test for fraud. So it's better to miss. This is, you know, how the justice system's supposed to work. It's better to miss a guilty than it is to charge an innocent. So that's pretty nice, pretty good. So yeah, its accuracy is pretty nice, but we did miss 30 out of 71 fraudulent transactions. So it could be better. Okay, so instead of having to have this all running, I will specifically be looking at this part. So make sure you actually fill these in with something that's not nonsense. And that'll be that. All right. Anybody got any questions or comments or concerns or math jokes or something else? Yeah, what's up? Use the exponential model for some of the data. We cannot get the values because it's too big. What's too big? Oh, I see. Huh. Is it working for everything below that? Or does it just not work? Well, you only have to figure out 1 and 2 meters. So as long as it works up to 200, you should be fine. So e to the 200. Ugh. Duh. Yeah, that should be fine. I don't know. Let's see how high we can go. Okay. I think there's a way to Python increase math range. Yeah, it's just an overflow. I mean, what are you going to do? But to answer the questions, you don't need to go that high. We got up to, let's see, 390. It's fine. I mean, there's more, this number is greater than there are stars in the sky. Okay, so you can get up to 390. It is what it is. Trying to think. What you could do is you could convert, yeah, do this. So convert the input data to meters. Yeah. I don't know why I didn't think of that sooner. So this is 0.001, this is 0.008, this is 0.036, this is 0.12, this is 1.2, so on and so forth. That should solve your problem. Because the question is actually asking in meters, even though the data is in centimeters, but we know how to convert. So yeah, you won't need to change the temperature, just change the centimeters to meters. So even the largest one, I mean, E24, it's not that big. I mean, it's larger than anything I'm going to ever deal with in nature, but as far as math goes, it's not that big. Okie doke. No problem. Have a nice holiday weekend.